So here is task one. So I'm just going to kind of explain how to do it. So first thing, we need to put in our graphs. Um, and we need to make sure that we're looking at what we want, right? So that's x versus time, as well as, I'm going to put in another one. Oh, come on. Oh, I want to move you. There we go. X velocity versus time. There we go. Now, if we look at these graphs, let's just make sense of them, right? So here, um, the graph starts out at a negative position, which makes sense because our origin is here. Also, the positive direction is to the right. So that's why our cart is in a negative position. Right? You guys see what I mean? Right? Because this is the positive direction. This way, the cart actually never gets to a positive position. Right? It just is in negative positions until it hits the end piece. And the end piece is right at 0. Right? So that's why at this time the cart reaches a position of 0. It bounces off and it starts moving in the negative direction again. Now, in terms of velocity, right, the velocity, and there's a little bit of error, right? That's why we see this up and down motion. But the velocity is pretty constant at positive, about positive 0.7 meters per second while it's moving to the right. And then after it bounces off, it's pretty constant around negative 0.5 meters per second because it's moving to the left, right? It changes direction. That's why the velocity reverses sign. Notice that it does slow down a little bit, right? And I think that's just because it's losing some speed due to friction, right? Because it's not perfectly frictionless. So the velocity starts out positive. When it bounces off, it switches to negative because it changes direction. Okay, so to use the x versus t graph to find the velocity while it's approaching the end, we can just fit a line, and we can look at the slope. Right, so we can see the slope there is about 0.66 meters per second, right there. Right, now for part F, it asks us to find the velocity using this graph, and if we look, right, it's, on average, it's right around the same, right, about 0.65, 0.67, right, so the slope of the x versus t graph is matching the value of the velocity versus time graph. And notice that when I found the slope, I just used that portion that we wanted. We would probably get a better answer if we selected this whole portion. But it doesn't change that much, right? Because the slope is pretty much constant because there's basically no acceleration. The velocity is not really changing by much. Okay, for part F, we are supposed to find the displacement of the cart from when it first leaves the hand until the spring touches the barrier. So to find the displacement of the cart, we want to take the area, right? We're using the v versus t graph, so we need to take its area. We can do that by highlighting there and clicking here. Right, so that gives us the area underneath that v versus t graph from the first moment in time until it hits the barrier. That's almost exactly 1 meter. Notice the units, right? It's meters per second, and this is like times seconds in the numerator, actually. So it's just meters, right? Because the computer is doing like, right, the multiplication of this area, right? This side is in seconds, and this is meters per second. And when you multiply those, you just get meters. So that's about 1 meter exactly. And if we compare this to the x versus t graph, the displacement over that interval, right? It starts at -1, and it moves to 0 almost exactly, right? So it makes sense that the displacement is positive 1 meter because it moved up about 1 meter in the positive direction almost exactly. Okay, lastly, for part G, find the acceleration of the cart over the whole interval for which data was collected. So the velocity is not constant. The velocity changes, right? And the velocity sort of switches abruptly. So we can't use the slope of this graph to find the total acceleration. Instead, we really need to use the definition of acceleration, right? So here, what we really have to do is we have to take our final velocity, subtract from our initial velocity, and divide by the total time. So the final velocity, I'm just going to kind of approximate it. The final velocity is about -5, or -0.5, and the initial velocity was let's say 0.66, I think it was about that. So minus the initial velocity, right? So minus negative 0.66. And then we have to divide that whole thing by the total time. So, and here this is not the best way to use a calculator, but I'm thinking on my feet. And the time difference between the final and initial moments is, if we look here, right, it's about 1, 2, 3, and I'm just approximating here. If you highlighted it, you could get a more accurate one, but I don't want this window to go away. So let's say about 3.246. I'm going to say 3.8 seconds about. Right, so that's our average acceleration right there. 0.04, and that would be meters per second squared. Okay, cool. I hope this video was helpful.